Hello everyone, welcome to the class of Calculus 3. And today we are moving to section 4.3, partial derivatives. First, let's take a quick look what a derivative is. Derivative, it is defined for a function of one single variable, and usually we write a function in this fashion: y equals f of x, and accordingly derivative can be denoted by y prime, f prime, or more commonly, this one is a little longer, but anyways, it is a little more common because it tells more information. dy dx, derivative of function y with respect to x, which is limit. And now in this section, we are really working with function of 2 or 3 or more variables. So accordingly, we're going to have those partial derivatives. In many ways, partial derivatives just are regular derivatives. You will see in a moment, okay? So first of all, we have the partial derivative with respect to x. And without thinking too much about the y, you really should consider this a function of x only. Or in other words, we are really considering y as a constant. Okay, y as a constant. So this is the derivative of f with respect to x. And accordingly, there are two ways to write this partial derivative. Many times we simply write this as f sub x, or use the Greek letter delta to denote the derivative ddx, df, dx notation. And similarly, for the variable y, we have a partial derivative with respect to y. We have the partial derivative with respect to y. It's written as f sub y or df dy. The d here, it is a Greek I believe that's a lowercase Greek letter delta. Yeah, okay. And essentially, if you read this definition carefully, we are really considering x as a constant. And that is really the essential part of partial derivatives. Okay, there are two partial derivatives. And to calculate partial derivatives, usually we don't start with the definition. We're just going to use the rules and the formulas. So this part, I have some formulas and the rules for regular derivatives. Indeed, they all can be extended to partial derivatives. The first one, it is the power rule, the derivative of a power function. The second one, that is the derivative of an exponential function, and derivative of the natural logarithm, and derivative of sine x, derivative cosine x, derivative tangent. For trigonometric functions, it is expected that you know very well about the sine and the cosine, then tangent. Okay, and also again for trigonometric functions, there are a few inverse trigonometric functions you want to know very well, like the inverse of sine. And also, if you know notation, sometimes we just write this arc sine, sine inverse, they are the same. And also we have cosine inverse or arc cosine, and tangent inverse or arc tangent. These are the derivative formulas. And I don't think that's a lot, right? Hopefully you agree with me. Those derivative formulas: power function, exponential function, logarithmic function, trigonometric functions, and the inverse trigonometric functions. But anyway, they are just limited. Each rule works only for one simple case. And many times we do have all those functions combined and mixed. So accordingly, you want to know some other rules about derivatives. This is a really must. Product rule, right? Derivative product. Derivative of u times v is u prime v plus uv prime. Derivative quotient. Somewhat really, I always remember product and the quotient together, because you look at the top, those two terms, they are in the same fashion. But for the product rule, you take a difference. For the product rule, you take the sum, I'm sorry. For the quotient rule, you take the difference. Certainly for the quotient, there got to be denominator involved. So it is denominator squared. And more importantly, for the derivative rule, okay, you need to know the chain rule. You need to know chain rule. We'll see how chain rule works in a moment, especially the chain rule involving with partial derivatives. Indeed, I think we do have another section. We were only talking about the chain rules involving with partial derivatives. So, this is the section of 4.3, partial derivatives. How about let's take a quick look at one example first. All the partial derivatives. And I believe I just took the example from the textbook directly. Okay, we are going to consider partial derivatives. I think it might be better if I just write in words, because part A, it is a function written in f, and then part B, it is a function written in g. So let's just say find the partial derivatives. F of x and y, this is a function of two variables, and then we have a few bunch of those terms involving x, y, and xy together. So to calculate partial derivative with respect to x, df dx, or f simply f sub x, okay, you are going to consider the other variable as a constant. So x squared, it's given derivative 2x, and then y as a constant. I have 3y together. 3y times x, the derivative is just 3y. And then, as I'm saying, be very careful about the notation. When we take the partial derivative with respect to x, we consider y as a constant. So this 2y squared, it is a constant. Accordingly, the derivative would be 0. It is 0 with respect to x. So this part is gone. But the derivative negative 4x, it is generating negative 4 here. Then for y, 5y minus 12, you may want to consider them together. That is a constant, right? Accordingly, derivative is 0. Derivative 0. I suppose this should be easy enough, right? Partial derivatives. Really, it's all about derivatives. And you really need to be very careful when you take one partial derivative with respect to one variable. You're going to consider or hold the opposite variables as a constant. So that's what I achieved here. Then also I have the another partial order derivative, f sub y, partial order derivative with respect to y. You consider everything about x as constant. So x squared, that's given 0. The negative 3xy, it's something times y. Accordingly, the derivative is negative 3x. Derivative 2y squared, the derivative is 4y. Negative 4x is gone because that's constant. Derivative 5y, it's just 5. Minus 12 still to 0. So I got the partial derivative with respect to y. And indeed, now we got both. I want you to take a quick look at together if all the partial derivative calculation makes sense to you. As I'm saying, really partial derivatives, they are just about regular derivatives. Certainly, you want to pay more attention for those notations. And the trick is when you take the partial derivative with respect to x, consider y, or if there are any other variables, they are all constants. And likewise, when you take a partial derivative with respect to y, everything about x, that turns out to be constant. How about let's take a break, and we'll be back in a minute. Thank you very much.